Now, turn to Section 4. You will hear a lecturer in sustainable design talking about biomimetic architecture. First, you have some time to look at question 31 to 40. Now, listen carefully and answer question 31 to 40.
Good morning, everyone. In today's session, we are moving beyond traditional building methods to discuss biomimetic architecture. Now, the term biomimicry comes from the Greek words bios, meaning life, and mimesis, meaning imitation. In an architectural context, it refers to the strategic study of nature, specifically biological systems and organisms, to find sustainable solutions for complex human problems. It is important not to confuse this with biomorphic architecture. While biomorphic buildings might look like a leaf or a bird in their outward appearance, they often lack any functional connection to the natural world. Biomimicry, however, is about function, not just aesthetics. The most famous example is the Eastgate Center in Harare, Zimbabwe. The architect, Mick Pierce, faced a massive challenge: how to keep a large office complex cool in a tropical climate without using a fortune in electricity. He turned to the world of entomology, specifically studying the mounds built by termites. These insects maintain a near constant temperature inside their nests, even when the outside temperature swings from 3 degrees at night to over 40 degrees during the day. The Eastgate Center mimics this by using a passive cooling system. This means it functions entirely without air conditioning. Instead, the building's massive concrete frame acts as a thermal sponge. During the daylight hours, this material absorbs the heat generated by the sun and the people inside. Then, as the sun sets, a series of high-capacity fans are triggered to pull in the chilly night air. This air travels through floor voids and eventually cools the heavy slabs of the building, preparing them to absorb heat again the following day. But biomimicry is evolving. We are now seeing the rise of living materials. One of the most promising is self-healing concrete. Infrastructure is prone to wear and tear, but by embedding dormant bacteria into the mixture, we can create buildings that fix themselves. When a crack forms and moisture enters, the organisms wake up and consume nutrients provided in the mix, producing a byproduct of limestone that seals the gap. If we can scale these technologies, we can drastically reduce the emissions produced by the construction sector, which currently accounts for nearly 40% of global carbon output. We are looking toward a future where our urban environments aren't just concrete jungles, but instead operate with the efficiency of a natural ecosystem.
This is the end of the test.